There's a hidden value for every piece of track that engineers worry about when temperatures rise: the critical rail temperature, the point where the risk of a buckle increases. It's not on the design drawings, but it's safety critical. One value that decides whether trains keep running or grind to a halt. But the CRT isn't just a threshold to react to. The factors behind this number are where the real engineering decisions sit, and where small interventions can avert major disruption to both trains and passengers. In this video, I'll take you through what really drives CRT, how these factors interact, and why the run-up to the summer months is such a crucial time to get some specific work done. To start with, for anyone completely new to the concept of CRT, it is the maximum rail temperature a section of track can reach before mitigations need to be implemented. Monitoring, speed restrictions, or, in the worst case, route-wide blanket speed restrictions. The key word there is rail temperature, not air temperature. On a hot sunny day, rail temperature can run significantly above the ambient temperature, which is why air temperature forecasts alone don't tell us the whole story. And crucially, CRT isn't one number for a route or even a line. It varies track section by track section, which is what makes managing it so resource intensive. So what drives that variation between sites? It comes down to four main factors, and it's here that decisions are taken that can influence how the summer period goes. The four main factors. The first is how the track itself is built. Is the site plain line or a switch and crossing layout? Thermal expansion behaves differently. Plain line acts as two continuous rails, while S&C includes free-ended switches and fixed points such as crossings. Construction also depends on whether the rails are welded together or joined with fish plates. Welded track is stressed to manage thermal forces, while jointed track relies on expansion gaps. The rail section itself, the size of the rail, makes a difference too, as larger, stiffer sections resist thermal forces differently to lighter ones. Sleeper type matters. Wooden sleepers are lighter than concrete and therefore require less force to move them. Sleeper spacing also affects the total weight of sleepers over a given length of track. And finally, fastening type. Different fastenings apply different tow loads to the rail, influencing how much they resist longitudinal movement. This is mostly a factor with older fastening types. All of these come back to the same thing: how strongly the track construction can resist thermal forces. And in practice, most of these are fixed at construction. You're inheriting the CRT consequences of decisions made years or even decades ago when the track was first installed. Beyond construction, geometry matters too. Curved track behaves differently under heat compared to straight track. Tight curves are more prone to buckling because the forces from thermal expansion push the rails outward. The sharper the curve radius, the greater the sideways pressure on the track, and the lower the CRT will be. That's why buckles are often seen on curves rather than in straight line sections. Then there's these all-important numbers. Welded rail is managed by its SFT, the temperature at which the rail is neither in tension nor compression, achieved by stressing during the installation. Jointed rail uses JCT, the temperature at which expansion gaps close completely. The CRT is worked out from either the SFT or the JCT, with an additional value added and adjustments applied for the other factors that we're covering. With no negative adjustments, this gives the highest CRT for a section of track. It's the starting point before anything else around a section of track is taken into account. And finally, the ballast. After SFT and JCT, ballast condition is the biggest single factor. Ballast plays a critical role in restraining the track in position. When ballast is disturbed, it loses strength until it reconsolidates under repeated train passes. Disturbance can range from a full renewal through tamping or stone blowing, right down to local manual lifting and packing. Each brings its own risk, from small weaknesses at the shoulders to the whole lengths of track that are now completely unconsolidated. Some sites may have consolidated ballast, but not enough of it, or it may be fouled or in poor condition. Both poor quality ballast and insufficient ballast around the sleepers again reduces its ability to hold the track in place. If you're heading into spring with a list of CRT sites to manage, this is worth knowing about. RailSense's TempSense provides continuous rail temperature monitoring, accurate, reliable data feeding straight to a dashboard via 4G, with alerts via SMS or email when temperatures approach your critical thresholds. No guesswork and no reliance on ambient forecasts alone. And here's the thing that matters at this time of year. TempSense doesn't require seasonal recalibration. While you're scheduling time and resources to recalibrate other equipment for the summer period, TempSense is already running. No intervention needed. For sites that need to meet the latest standard, the TempSense Enduro is fully compliant to Mod 14 requirements, with season-long reporting every 15 minutes, so you're covered from day one. Combined with BuckleSense for continuous track position and movement monitoring, RailSense gives you eyes on your highest risk CRT sites 24/7, without boots on the ballast. Head to railsense.co.uk to find out more. Link in the description. I started this video by saying that CRT is the number all track engineers worry about. But why? Firstly, it sets out the risk high temperature poses for each section of track. The lower the CRT, the higher the risk of a buckle, and the more management that section is going to take. And CRT isn't just important on the hottest days. In the run-up to summer, CRT values drive maintenance priorities. Engineers focus on sites with low CRT numbers. Only some of the factors we looked at can be remedied, unless the track is fully renewed. For maintainers, this often means restressing CWR with low SFTs, or resetting joint gaps on jointed track with low JCTs. Ballast plays a part too. Fouled ballast, like wet beds or areas with low shoulder height, need to be dug out or topped up. Now that might sound simple, but in practice it means planning the excavation and replacement of tons of stone. Then once the hot weather arrives, the game changes. Engineers have to make tough decisions about whether to disturb ballast to carry out other maintenance work. Any disturbance weakens the stone until it's reconsolidated, which means the site must be closely monitored and managed. So every job becomes a balancing act. Is the work urgent enough to justify lowering the CRT in the short term? Or is it safe to hold off until the conditions ease? And when mitigations are brought in, they carry their own impact. Monitoring is now mostly done through remote systems, giving real-time data on rail temperatures and conditions. But even with sensors, staff still need to be deployed at times, checking sites in person or implementing speed restrictions. And when speed restrictions are imposed, they often start small, but can escalate. First to individual sites, then across wider areas if the hot weather persists. What begins as a local precaution can quickly snowball into a network-wide constraint. The short notice implementation of speed restrictions forces adjustments to the train timetable, even with forecasts and knowledge of the sites at risk and their CRT temperatures. It's hard to accurately predict when the speed will be imposed. Not exactly helpful when you're trying to plan a train service. For passengers, this shows up as delays and cancellations. For freight, it means they can be held to allow passenger services to continue to run, delaying them as well. The ripple effect spreads far beyond the piece of track where the CRT was exceeded. CRT isn't a universal number. It varies site by site, shaped by some factors locked in at construction and others that can be managed through maintenance. Sometimes, CRT is even temporarily lowered as a result of the work taken to fix another safety critical issue, forcing engineers to balance risks on the ground with the impacts on the train service. It's a number that engineers watch all year round, and one that operations teams keep a close eye on when the summer heat arrives. CRT is both an indicator of risk and a measure of the disruption needed to keep trains running safely. One hidden number, but one that can make the difference between smooth running and a buckle. And if you want to dive deeper into how geometry drives these kind of risks, I've put together a free track geometry email course. It'll walk you through the fundamentals step by step. You can sign up using the link in the description and in the top right hand corner now.